All right, welcome to our afternoon session. We're going to lightning talks. We're going to begin with Andy Lee, and he's going to be telling us about VQE for the square-octagon-lattice Kitaev model.
Okay, thank you.
Yes.
Okay.
No, you can control this.
Okay, thanks. Thanks for coming to my talk. So I'm going to talk about VQ application on the square-octagon Kitaev model. So this one is SQMS with the algorithm team. So there are a lot of people here. I mean, yeah. So those are the our SQMS algorithm have on this. And then so we have like for this particular talk, we actually have like two archive between. So let me start with the a very small background on the Kitaev model. So Kitaev is famous for magnetic model, but we are specifically talking about this like Kitaev spin model that has been proposed back in 2006. So the idea of this Kitaev model is that so this is a spin model. Each of the spin is coupled with the other spins. And for each of the coupling, they have like different type of like coupling. So they have like SS coupling, Y-like coupling, and CC coupling. So why is it interesting is that I mean this model, I mean, although I mean all of this like J, they are positive. So I mean the coupling is fermionic. However, the fact that there are different like type of coupling, so that effectively there is an extreme frustration. So that if you look at the ground state of this system, I mean, then there will be a spin interface. So this is like pretty interesting. In particular, I mean, this model is particularly interesting for the viewers is that because this model indeed is exactly solvable when using Majorana fermionic mapping. Now in this, you can see that I mean this very important feature of this model is that I mean each of the spin is coupled with the other spin with like a different type of coupling types, so that it actually can be generalized to not just for the honeycomb model, but it can actually generalize to a class of different 2D spin lattices. So in particular, the one that we are looking at is the square-octagon model. The reason why we look at this model because we are thinking about VQ application that could be directly or natively applied on the Variational QPU. So we look at this like in the middle here, we have the square-octagon-lattice. So you compare this with the SP9 QPU or more recent SP9M1 QPU. So they actually have this like square-octagon structure. So if we consider answers that would be we mainly have this like connectivity, right? So that will be much easier to apply the square-octagon application on the Variational QPU. Now, I mean, we consider some slightly modification for the Kitaev Hamiltonian. Well, because I mean, this Hamiltonian itself is slightly solvable. So why we like to determine the class at all, right? So if we want to consider some maybe a little more realistic system in the sense that I mean, when we consider experimental study, right, there could be people would like to use, for example, external magnetic field to probe the system, right? So we, in addition to the Kitaev Hamiltonian, we modify this with like additional external magnetic field, so that I mean this Hamiltonian is no longer as solvable. So we would like to try to use VQE to solve for the ground state of this particular Hamiltonian. Okay, so VQE. So I mean the most important point of the VQE is actually look at what kind of like variational answers we would like to apply, because this is really the most, I say, the only one of the most crucial points that will determine whether VQE will be successful or not. So we try for this particular, we try two different VQE answers. One is the Hamiltonian variational answer HVA, and the other one is the hardware variational answer HEA. For the Hamiltonian variational answer, the idea is really just that I mean we look at the Hamiltonian here. There are basically 6 different types of terms. So we take each of the terms and then attach a parameter with it, and then expatiating them to do each of the terms here. So we have like such different block here, which each of the block here will correspond to one of the terms in the Hamiltonian. And then so we repeat this multiple times and call this NAS. So this is sort of like a simple HVA that we can apply. Another way is that we look at this like hardware, and we see that okay, there are specific gates or it's particular 2 cubic gates that are native to the hardware. So we try to maximize the utilities of the hardware. So this is the well-known hardware efficient answer. So we basically just have the native 2 cubic gates, and then we before after that we append arbitrary single cubic rotation to it. So so you can see if we look at this like number of two cubic interaction and the number of parameters, you can see that there may be advantage by using HBA in the sense that number of parameters only depends on number of layers, but not on the system size. So there may be from this, there may be reason to believe that HBA could be more scalable compared to HDA. We'll see in the simulation. Okay, so what I'm showing here is basically a noiseless simulation. We want to benchmark how two of these answers will work. So we actually use the Bubacco and CMAES together with multiple initial values so that we can better get a theoretical minimum of the verbal answers. But we can see that probably still some optimization issue that we have to be careful. But nonetheless, here what we're doing here is that first of all we're trying different number of strings. So we have start with 4 qubits, and then we have two examples of 8 qubits with different parameters, and then we also have a 16 qubits example that we apply BQ on. So you can see, except for the top left figures, that is a very simple example. So that's probably too simple to actually tell how well the BQ actually do. But if you look at the other example, we have the 2 8 qubits one and 16 qubits one. What you tell us, except for the very simple case that we only apply one layer, so that in that case, where the flexibility of hardware efficient answers give us an advantage. Otherwise, it is almost always that the HBA will perform better. The reason here is actually pretty simple, because of the fact that we have small parameters in the HBA, and therefore it's actually easier to optimize it. So I would claim that what we can see the advantage really from the fact that it's easier to optimize. But nonetheless, so I have 2 circles here in the bottom left figures here. So I see that actually is some signature of the optimization issues, right? Because you can see that in principle, when increase number of layers, the answer should be at least give me simple performance with a small number of layers answers. However, you can see that the performance actually become worse. When I increase the number of layers, it's really a signature saying that the optimization is still an issue. So also in principle, what one could do is that we can do more initial values, or we can figure out maybe some other more efficient optimizers. But that is not trivial. We actually have done quite a lot of study to decide what optimizing strategy we are using. But one that will be a more complex system. This is so an issue. It's not surprising. It's probably something that is closely associated with the well-known parent patrol. Nevertheless, so let me put here. So so in the previous batch, probably doing this on a Castle computer, we're doing a lot of simulation. So we actually try to figure out whether it's possible to actually apply something on the QPU and see how well we could go. So we tried this by doing the simplest example. We try to apply a single 1 layer HBA answers on just a qubit and see what will be the result here. In order to get a very first understanding of how well the result will be, we just p-optimize the answers on the Castle computer. So we take, for example, the value we got in the previous benchmark, and then we use this p-optimized answer and then run this circuit on SV9. So we implement the multiple element integration. We do a lot of serial extrapolation. We do randomized compiling, and then we do a standard VLL integration. So what you can tell from this graph here, so this is a graph showing that with different scale factor corresponding to the serial extrapolation. So we extrapolate back to the fact that to the form which is within the model is corresponding to the serialized limit. Unfortunately, with all this integration, we can see that the result is still far away from what we can get from simulation. So the result we get is minus 1.36. And simulation actually has a much lower value. So this is really telling us that the error mitigation we apply is not sufficient to mitigate the infidelities exhibited in the device. Let me say a little bit about main challenges we see from this simple study that we had. So first of all, when we actually think about implementation, then it's clearly that we need to think a little bit more about what we could do with the noises on the list devices. So in principle, we have applied a more sort of general arithmetic gauge lattice. So we probably, from what we can tell, right, in order to make this one actually work on the current device, we will have to think a little bit deeper to see whether it's possible to have like more hardware and model specific arithmetic. And then also, I mean, this could be like on top of this is that hopefully is that if we actually like optimize our answers on the QPUs, then some of this control and coherent errors may be mitigated with the fact that automatically by the optimization. So those are two things that could make the thing better. But I think there's many more important issues about the optimization of this variable answers, because I mean, this is really the point that decide whether it's possible to actually scale up the application to the economic advantage. So as I said before, there seems to be optimization issues. So one path to go forward is, I mean, there have been studies about over parameterization. So that is the idea that, I mean, now, I mean, we have like relatively small number of layers, and then number of parameters is at most of the order of hundreds. So there have been studies on other, for example, spin models, or in general, I mean, this idea is actually coming from a classical deep learning model. Is that in principle, if we increase the number of layers a lot, and at some point that, I mean, there seems to be could be like a phase transitional behaviors, the optimization suddenly become easy again. So that's one way to think about this. Maybe if you just increase the number of layers a lot, and then maybe the optimization will be easy. And the other part that actually I look forward to talk about this is about maybe we should actually take an even deeper look to some model specific answer. So I mean this one I'm going to talk about, to think about this from the Majorana fermionic representation, whether it will give us answers that would be easier to optimize. Okay. Yeah, so here the idea is that we are going to use the knowledge about this like Kitaev model that in fact is exactly solvable without external method. It's exactly solvable using this Majorana fermionic representation. So the idea is that so in general you can on the top here, okay, you can see this is basically Kitaev model without external magnetic field. So if we introduce Majorana representation, so we basically use like 4 Majorana fermions per side, and then we can do all the standard transformation. Then ultimately you can see that, I mean, this Hamiltonian can be written down as a like 3 fermions model. Okay, so I mean, and then from that, I mean, if we with only this model, then I mean that will be so the k here will, the value of k here will be correspond to fixed gauge, so that ultimately you can like reduce the whole model by representing this model in a particular fixed gauge sector with just using n over 2 complex fermions. So that's the idea of how to actually exactly solve this model. So right now inside we can think about, okay, now I mean the previous model is solvable, but then we can actually include extra interaction while those interactions will still preserve the gauge. So for example, there's basically one particular example here is that this is motivated by the fact that we can actually get these terms doing this perturbation of big magnetic field. But nonetheless, I mean, this we just look at this particular term, and then if you rewrite this in terms of the Majorana fermionic representation, you can see that one can show that this term together will still preserve the gauge. But nonetheless, I mean, it gives some non-trivial interaction, particularly in the last term here. You can see that this is basically a 4 fermionic interaction. So I mean, this motivates to actually write down an ansatz that will based on this particular this, and together with the previous the 2, I mean, the 3 fermion model, it motivates to actually write down VQ answers that includes this like 2 fermion tones, although 4 fermion tones with parameters that to be optimized. So I mean, the idea is that with this answers here, so for the implementation, then what should we do is that we start with the Majorana fermions, and then we transform this to introduce the AJ there, and then transform to complex fermions, and then we do a Jordan beta and transform to speed. So that is I mean, this is like some of a rough idea of implementation probably can be optimized, but I mean, this is at least a way to do so. And I didn't write down a specific work to think about, but I mean, you can also generalize this idea if we have like long gauge preserving interaction. For example, if we have like external magnetic field, then it will actually miss the gauge. So we could also generalize the idea. Yeah. But nonetheless, I mean, this particular limit that I mean, when gauge is that preserved, right? So then we actually see that, I mean, so for the top panel, I mean, you can see that we first of all we start with like capital intact should be 0, meaning that we only have like 3 fermion times. Then you can see that this actually this answer gives us numerical in terms of numerics. I mean, it's basically a set solution. So I mean that is already promising, but I mean what's more important is that when we include the interaction term before body interaction term, then we can actually see that I mean the error here is like it's still pretty good. I mean when we compare to what we had before in HVA or like hardware efficient answers, I mean this is like automatic factor, and not just that. I mean because of the fact that we can all reduce this to just n over 2. I mean spin, right? So we effectively this like we could is actually also much easier because of the fact that we only require half the number of qubits. So it's also with all this implementation, I mean it's also clearly is easier to optimize. So give me a quick summary. So so if we just look at this like the HVA and HVA, right, then we can tell okay, HVA is probably easier to optimize. I mean this is I would say that because we take some of this like model information into the answers that we decide answers that is that have some information about the models that make it easy to optimize. But then I mean this is still to the fact that I mean it's not the best one. So to think about this, so I mean we actually can go one step further to look at this like Majorana fermionic representation, and then it is not just easy to optimize, also require half the number of qubits. So it's appear to be the fact that I mean if we take a little bit more information from the model, I mean that could be the way that how we can push forward the VQE toward maybe an advantage. Ultimately for the in order to actually implement any of this, then for the experiment, then we probably need to do more study on the specific error mitigation. And then so and this presentation is based on the 2 papers that we put on archive. So I mean this particularly the fermionic representation is like lead by Emma, and then so we recently put it on archive. Thank you so much.
Questions? And I'll abuse my power and ask a question. So, you know, there's a lovely, it's in the first part of your talk where you had experimental results. You know, there's a nice simple circuit to diagonalize the model. Did you, maybe I was thinking it would have been interesting to have compared, you know, data from that versus these other Ansatz.
You mean simple to diagonalize? You mean that I have the Hamiltonian?
Yeah, so it's hard for me to understand what the number -1.36 means because of the conflation between algorithmic error and noise error. And I know that if you, for example, ran the you know, Kitaev's diagonalizing unitary, then there's 0 algorithmic error, and I can then thus kind of mod out algorithmic error and get a number. And
yeah, okay. Sorry,
I don't know, or yeah, alternatively, if there's like some other observable.
I should explain it clearly. I mean, we have the result here with -1.36. The simulation actually we want the same circuit and obtain the energy value there. So the -4.23 is the value that if we have the circuit with to be implemented without any noise. So the difference here is is hardware error. And then we also diagonalize the Kitaev model that is something like give us -4.6. So the difference there will be the error. So it will be improved if we go deeper, but then due to the fact that I mean the hardware is already so noisy. So at the end of the day, we will have.
Got it. Yeah. Other questions? Yeah.
So have you compared the circuit depth of the fermion form? Because for its fermions, we generate a lot of power.
Yeah, that's an excellent question. Yeah, that is like I can't remember the exact number, but it definitely, I mean, if we want to implement the fermionic representation answers, due to the fact that it's going to first of all we have the fermion, and then we do transformation to like complex fermion, and then do Jordan Wheeler. So you can imagine that this answer will be very complicated to be implemented actually if we want to use the cubic gate. And I can't remember the example, but it definitely requires like at least a few hundreds to cubic gates, to actually implement the fermion, the answer in the fermion representation. So that is like will not be. So if you consider like implementation of hardware, it probably will not be right now. There will not be advantage to actually use that answer due to the fact that there will be too many 2 cubic gates. But in the future, if there will be improvement in terms of the fidelities or the more arithmetic equation, and we think that there will be advantage to try to use that like fermionic representation answers. So because
the number of qubits.
yeah, it had to have number of qubits, but still, even with the high number of qubits, we still have like much larger number of 2 cubic gates, and that is like the major error source that makes it difficult to be implemented right now on the current device.
All right, let's thank Andy again. So the schedule says that Sabri Kais is supposed to be our next. Sabri, if you're there, speak up. Otherwise, we'll actually go ahead and get back on time and put Carol up here.
Hi. Sabri is not here actually, but I'm going to speak on his behalf.
Okay, great. Great, thank you.
So can everyone actually see my screen?
Yeah, we're transferring you over to the main screen. Give us just 1 second.
Sure.
To troubleshoot. And we have you on full screen. So take it away.
Hi everyone. This is Manas Sajjan. I'm actually a postdoc at Purdue University, and I'm working in Professor Kais's group. So the topic of discussion which I'm going to talk about today would be how to encode a neural network, a representation of a quantum state for molecules and materials, and how to train that state by using a quantum computer. So our objective here is actually pretty general and standard. We're given a system. System can be any one of the following, and that system comes with basically a Hamiltonian, which is a D cross D matrix. We want to construct approximate eigenstates of that system, and we also want to filter these eigenstates based on symmetry operators OI, which happens to commute with the Hamiltonian because these are symmetry operators. So that's basically the definition of the problem that we're after. And the approach which we are going to take happens to be this. We're going to construct a variational ansatz, which is going to encode the state onto a neural network. So that's the machine learning component. And we're also going to train the ansatz by using a quantum circuit. So that's the quantum computing component. And the outline of this talk is going to be does this. We'll start with a brief description of the algorithm, and then we're going to talk about the resource requirements of the algorithm, and then show some applications into the ground and the excited states of molecular systems as well as 2D materials. So let's start with the algorithm. Now, what is the machine learning component of this particular algorithm? We see that we have basically 2 parts to our answers. The first part is encoded within a blue box, and that happens to represent a neural network, which is commonly known in deep learning community as restricted Boltzmann machine. It is essentially a graph which connects two spin registers. One of them has been denoted by sigma, and the other has been denoted by h. A's and the B's are like the local magnetic field or the biases at the spin registers, and the Wij matrix elements are the interaction between the two spin registers. The distribution that we'll be interested in is going to be the thermal state of a classical Ising Hamiltonian, and that will be encoded in this particular neural network. The two other neurons that we see here is going to encode a function like this, which is going to take care of the phase of our wave function. So together, this particular distribution is going to only encode for the amplitude field of our wave function, which is why it sits as a square root here after we have traced over the hidden neurons. And this particular function is going to encode for the phase field, and the sigmas are basically the computational basis vectors, which are essentially bit strings. So the product of these two functions is going to define the coefficients of our wave function, with the tunable parameters being A, B, W, D, F, C, E, etc. So the broad overview of the algorithm is this: we'll initialize the parameter randomly, then construct the amplitude by using the RBM part of the distribution, construct the phase by using these two neurons. That allows us a state preparation procedure, and then using the state, we can construct a cost function and check for its convergence or update the parameters by using any gradient-based methods. So where does quantum come in all of this? The quantum comes in the state preparation procedure, especially in the construction of the distribution that is going to encode the amplitude field. And the cost function that we're going to use is going to be specific to whether we're doing asymmetric filtering or we are just interested in one of the eigenstates. And that I'm going to talk about on a case-by-case basis. So as far as the quantum circuit is concerned, this is the circuit that we're going to use to construct the amplitude field. The circuit demonstrates a specific case in which we have two visible neurons and two hidden neurons, and the circuit also requires m into n, or 4 ancillas in this case. The first part of the circuit has a single qubit RY gates, which are all parameterized by the local biases A and the B, and hence the state at the point A is essentially going to be the non-interacting part of the distribution. The state at the point B is going to encode the interacting part of the distribution, where the interactions between the visible and the hidden node are stored as amplitudes within the ancilla. And we see that if the ancillar register after the state B, or after the point at state B is now measured and allowed to collapse in state 1, that is only the measurements where the ancillary register have collapsed in state 1 are post-selected, then we have the product of this function and the function eta, which is defined as this, and that happens to be the exact distribution of the amplitude field that we want. We see that there is also an effective temperature here in the form of 1 by k, and where k being a real number. I'm going to come to shortly to the role of this particular real number. So as we have explained that if we want this algorithm to be successful, we want only to post-select the measurements where the ancillas have collapsed in state 1. And we actually deduce in this paper that the probability of success, that is the probability of the ancilla collapsing in all state 1, is actually upper bounded by this particular number, which is defined only in terms of the parameters of the neural network. And we can attain, say, several limiting cases depending on the relative values of the parameters. The K, or the effective temperature, is used to actually make this particular lower bound greater than a certain number. So we choose K so as to boost up the probability of success beyond a certain number. And thus, the resource requirements of our algorithm happens to be this: we require m and n qubits to encode the two spin registers, as also m into n ancillas, because we also want to encode the interaction matrix elements Wij between m and n. And since there are m into n Wij elements, there will be m into n ancillas. The number of gates is also that, and the number of parameter count is also of the order of m into n. Thus, our algorithm is basically quadratic on all fronts. And now let us see at an example, especially when it comes to 2D materials. So that is going to define the material component of the talk. So we're going to specifically focus on TMDCs, which are specific kind of 2D materials where the unit cell happens to have a D3H symmetry like this, with a one layer of metal atoms sandwiched between two layers of chalcogen atoms, and the corresponding unit cell in reciprocal space is also an hexagon, and we're going to specifically talk about the band structure in the gamma K M gamma part. The Hamiltonian that we're going to use is actually from this particular paper, which shows that if we just use the three metal d orbitals, that is a good enough effective model for a wide variety of TMDCs as far as the valence band and the conduction band and at least one higher order band is concerned. The blue result corresponds to the 3D orbital model, and the red result is that from an exact DFT calculation. So if we were to use that Hamiltonian and use a cost function like this, where O can be basically a ground state projector, effectively for getting the conduction band, we're going to search in the space which is entirely orthogonal to the ground state, with omega being 0. So we can actually see that all flavors of the RBM representation can represent the band energies for both the valence and the conduction band very accurately. But RBM CL is basically the classical computation of the RBM. RBM chiasm is basically on a simulator, and RBM IBMQ is a specific IBMQ hardware where we use IBMQ Toronto. The energy errors are here, and the infinities of the state constructor using the RBM Ansatz is here, and both of them are pretty low. A similar result were also obtained for WS2, another TMDC. And if we focus specifically at the K point where the band gap is basically minimum, we can also construct the state composition from the RBM representation. We see that at the K point, the conduction band in both MOS2 and WS2 is made entirely from the DZ square orbital, whereas the valence band is made from the superposition of DXY and DX2 minus Y square. This is also the result which has been seen in this particular in the same paper, where they show that the valence band is made from DXY and DX2 minus Y square, whereas the conduction band is made entirely from DZ square. And we can further actually spin orbit coupling. The conduction band do not split much in this particular model, but the valence band does quite a lot. And we see that the energies of the two spin split valence band can be computed with very low error, as well as the states of the spin, the amplitudes of the metal d orbital on the spin split valence bands are also close to what it should be from the exact results. Now, and we also filter states based on symmetry. Since TMDCs have a D3H unit cell, they have a C3 axis along the ZA direction, and hence LZ is a constant of motion. In the basis of these three orbitals, LX and LY matrices are actually null matrices. And so we can use L squared, which enjoys exclusive contribution only from LZ as a symmetry operator. These are the three eigenvalues of L squared, and these are the three eigenvectors, and these are the states to which the eigenvectors correspond to. So we see that if we were to use L squared as a symmetry operator and put an eigenvalue of 0, we should expect the conduction band. And if we use L squared, if you use an eigenvalue of 4 and also demand that we get the minimum of the 2 energy, we should get the valence band, because this is a band which is above the conduction band. So that's exactly what we're going to do. This component is going to define the minimum of the 2 energy, whereas O is going to be a symmetry operator, and omega is going to be the corresponding eigenvalue of the symmetry operator that we want. And we see that if we do that for MOS2, we can filter the state. This is the exact result. And these are the three results from 3 different RBM computations. The energies of the states happen to match. The constant violation, which is omega equal to 4, omega equal to 0, happens to be quite low. And the energy error from the exact one, which is 1, is also quite low for all three flavors. The infinity is low. Similar results are also obtained for omega equal to 4 of eigensector, where we get the valence band, and hence the energies are all negative. We also see something similar for WS2 as well in both the eigensector. So far, we have specifically spoken only about TMDCs and 2D materials. Now we're also going to speak about molecular systems, which are basically strongly correlated under the effect of geometric distortion. So as a prototypical example, we choose at the water molecule in the S2-XG basis, we choose an active space of 4 electron and 4 orbital, where we have the HOMO and the HO-1 and the LUMO and the LUMO+1. And we construct the ground state and 2 excited states, and we also group the excited state using asymmetry partitioning into a singlet and triplet. And we see that in all cases, the Harbium values happens to match with the exact Cassier results, and these are the infidelities of the state, which is 1 minus the fidelities. And we are plotting it by actually distorting the bond angle over here, which is defined as theta. We can do a similar calculation for the excited state of a C2H4 ethylene, and we do this by actually etching the CC bonds. Since both the pi and the sigma bonds are broken, we actually choose an active space of these 4 orbitals, where this is the HOMO, this is the LUMO, and this is a sigma antibonding. This is basically a sigma bonding, which is deep-seated and occupied. And if we use again this 4 electron 4 orbital basis, where these 2 are the occupied orbitals, we see that the RB results are actually in quite close proximity with the Cassier results, and the infidelities of the states happens to be this. This state, by the way, is basically a singlet. So here we have encoded a neural network quantum state as a variational ansatz, and we have trained it using a quantum circuit. We have actually calibrated a results for materials using TMDCs, both with and without spin orbit coupling. We have also studied the effect of asymmetry partitioning on such systems. We have studied examples on molecular systems as well. In the same paper, we have also seen that what kind of error mitigation scheme can actually improve her performance, and we have also calibrated the results by varying the hidden node density. I'm actually discussing those results over here because of time, but in case if somebody is interested, we can talk. So the road ahead is essentially reducing the cost of the algorithm. Our algorithm is basically quadratic, or order n into m, where n is the size of the visible node register and m is the size of the hidden node register on all fronts. While it is already quite okay for gates, it can be further reduced when it comes to the qubit requirement. So that is exactly something that we are working on. Then we are also working on bandgap engineering in TMDCs and also quantum phase transition. This is also an ongoing work. So I'd like to acknowledge Professor Sabrakais and of course the entire KAIS group, and also the funding from the Quantum Science Center at Waterloo. So thank you all for your attention. And I'll be more than happy to take any question.
Thank you, Manas. So let's get Carol to come up here while we take a question. Any questions? I'll ask a quick question. I guess what you've modeled with the RVM is basically a band structure that comes from a tight binding model.
Yes.
Can you? So that seems reasonable. Can you comment? Can you comment on generalizations more, or yeah?
Yes. We can actually study the effect of electronic interactions within materials. We can actually augment the tight binding Hamiltonian by using say a Hubbard type of on-site interaction, where two opposite spins are going to feel a potential U. Also, we have demonstrated for the case of a molecule where we have an explicit electron-electron interaction, as is seen from this slide, and we can construct the ground state as well as the excited state as well. So this method is actually quite general and can be used both for materials and molecule. It's just for materials is a band structure which is often of great importance, whereas for molecule we can construct the entire potential surface depending on the degree of freedom, which in this case happens to be the bond angle in water. But we can extend this to systems which are correlated as well as not correlated.
Thank you. All right, so next up is our last, we saved the last for the.
Are you sure
That's
that
for
you
last.
don't want to reschedule it for tomorrow? Because people might be driving right after. I don't know if we have enough time to get to the hotel. Your decision.
Yeah, so let's comment on that for one moment. The Hotel Park Central is just a mile down the road here. Some of us who are staying there have walked back and forth, and it's not much of a problem at all. I think I'm sure that is everybody good with getting over there? And let's give Carol 10 minutes, and I think we still have plenty of time to get over there. We could take our time starting dinner, and so.
Okay, let's get started without further ado. So I will keep everything within 10 minutes or less, I promise. So today I want to walk you through the coupled cluster downfolding procedures and say a few words about the possible applications in the quantum computing. So what is a downfolding procedure? It's a very general term. It's basically any many-body technique which can squeeze the dimension of your Hamiltonian or your problem into the active small dimensionality active space. And the corresponding effective Hamiltonian which works there is supposed to reproduce the energy obtained in the diagonalization of the full Hamiltonian in the full space. So, oh, nice. I love the.
I'm not familiar with this notation.
It's a new one. This is actually new physics. So anyway, I wanted to say that I will be talking about the two types of the downfolding, the non-Hermitian downfolding and the Hermitian downfolding, which is a candidate for the quantum computing. But in both cases, the way how we construct those effective operators are the consequence of how we represent the wave functions shown here and there, right? So the first one is actually the standard coupled cluster expansion. The second one is a double unitary coupled cluster ansatz. So we have two types of the wave function parameters. One, the active, one the internal degrees of freedom, which basically correlates your system within active space. The external degrees of freedom, on the other hand, just correlate your active space with the rest of the world. Okay. Oh, it's almost there. So let me go through the properties of the downfolding, and I will focus on the properties of the non-Hermitian. We have equivalent results obtained also for the Hermitian case. So it's a little bit more complicated because of the more complex algebra behind anti-Hermitian operators and the standard operators we are using in the cluster, which are nicely commuting with each other. So the first important message is that in coupled cluster, you can probe the system with any subsystem described by some active space. So what does it mean to probe? So we can build a circle-quantized representation of the effective Hamiltonian, which acts in that active space and gives you exactly the same energy as you would get in the coupled cluster calculations. And there are many, many classes actually for each system, for each coupled cluster approximations of those subspaces. So in fact, if you look at the structure of the effective Hamiltonian shown here, this reads like external, You recognize physicists, basically the basic traits of behind the different renormalization procedures, because in the effective Hamiltonian, you integrate the external degrees of freedom. And basically you have flexibility to apply this formalism to any type of the active space, which describes some subsystem of your full system. This is very interesting, but even more interesting is the way that you can actually couple those problems corresponding for the different active spaces into the flow. So you have a coupled small dimensionality eigenvalue problems. And it turns out that at the solution of such a flow equations, right? Your solution of those equations, the flow equations, are equivalent to the standard coupled cluster equation with the cluster operator, including all the internal excitations corresponding to the different active space problems. So now it real fun starts because the inverse statement is also true. So we can say that for certain types of the cluster operators, you can represent the big problem in the form of the couple low dimensionality eigenvalue problems. So this is exactly what we would like to happen in the quantum computing, that you can probe the bigger space by small dimensionality of the problems. And this is possible in the standard coupled cluster. This is exact. We can mirror those. We can mirror those algorithms also in the case of the Hermitian case, which involves a little bit more complicated algebra because you don't have all the things commuting, but you can represent in the Hermitian case things in a similar way as here, right? Whatever it is. So this stuff is this way of dealing with the equations. Is also a nice way to encapsulate, to describe the sparsity of the system, because for each subsystem you have a small effective Hamiltonian. You can form the density matrices, and based on those density matrices, you can select the most important degrees of freedom for that given subsystem. And this is intuitively very kind of understandable in the realm of the chemistry, but how you can utilize sparsity, for example, in the nuclear physics or condensed matter physics is less obvious. And I guess this might be something that might help to get there. Okay, I hope. Wow, back to normal, right? So I guess I use the PDF kind of spin copy. Anyway, so we can generalize everything to the Hermitian case, where we're using this W unitary coupled cluster ansatz, and you can show in a similar way that as in the single reference coupled cluster theory, that you can form the effective Hamiltonian, which should give you the same energy as the big problem, right? In this case, because of the lack of commutativity, blah, 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 this expansion is non-terminated. So if you want to make some practical use of this, you have to come up with the approximations which approximate this expansion and approximate this external part, right? And I guess we have some ideas how it can be done. For example, we are using the commutator expansions for the approximating those non-terminating expansion, the finite rank expansion. We are basically retaining only single and doubly excited up to two-body terms in those effective Hamiltonians. And we take we approximate the external degrees of freedom through the standard coupled cluster single reference calculations. Those approximations are justified if you go and do some analysis behind that. But I would need another 5 minutes to talk about this. So this is the first example. It has been done in collaboration with Microsoft and WK and QDK interface. We are showing that basically using the quantum phase estimation, the green dots are the downfolded energies are very close to the Fursi exact energies obtained with 30 orbitals. While for the active space for the downfolding we use 4 orbitals. So we quickly realized that actually single commutator expansion as used for the hydrogen 2 H2 doesn't give you good accuracy for the bigger system. So this is lithium 2. This is lithium dimer. And this is how it works. Red squares are the energies of the diagonalization of the effective Hamiltonian, the bare Hamiltonian in active space, way off from what is represented by the bottom curve, CCSD T obtained in the 58 orbitals, much bigger space. And you see that the green curve, this is the single commutator expansion, isn't bad, not perfect. But if you do the double commutator expansion in this active space defined by 10 active orbitals, you're getting pretty close to what is deemed to be exact. Okay, so this is water. So we basically demonstrated that by increasing the active space size, we can get pretty close to the CCAZTQ results within the 58 orbitals. So in our calculations, in the largest, we used 16 active orbitals. So you see that a lot of savings, at least in terms of the qubit that you need to use in those calculations, right? So there are two obstacles. I mean, the problems, if you really want to get those downfolded Hamiltonian working, you have to be able to deal with the complex complex algebra behind the Feynman type diagrams to define the downfolded Hamiltonians. So we developed for this purpose some symbolic tools to deal with the weak theorem, and what it does also is convert those expressions, algebraic diagram, the algebraic formal diagrams, to the language digestible by our library, parallel library, tensor contraction for many body system TAM, tensor contractions for many body methods TAM, and in effect we can translate it into the parallel codes, which have a lot of flexibility. We can play with the, we can go beyond the binary contractions. We can do multiple commutators, and we can take advantage of the big summit system of Oak Ridge, hopefully Aurora pretty soon. This is the current effort. So we are kind of connecting the dots. We have already the symbolic manipulator working. This has been already integrated with the tensor algebra library, and currently we are working on the integrating the whole framework with the different quantum solvers, QDK Microsoft, density matrix simulator I will be talking about, and solvers provided by Oak Ridge. There are other options. We have homegrown kind of solvers based on the connected moment expansions. So those things will be explored pretty soon. And last slide is a great team with a huge synergy. So this is a really nice collaboration between the PNL team and Microsoft. So 10 minutes. No questions?
Let's go to dinner.
It's
And that's
the best option, the best idea.
Thank you, everybody, for your patience. Let's go to dinner.
Yeah, so just do that, and if you open, yeah, it has an on product.